Welcome to a video on quadratic inequalities. I'd like to start by taking a look at the graph of a quadratic function. Before we talk about where the function is positive or negative, let's first talk about where the function is equal to 0. Remember, when we're talking about function values, we're talking about y values. So the x-intercepts represent where this function is equal to 0, here and here. That means everywhere else the function must be either positive or negative. And if it's above the x-axis, the y-coordinates would be positive. Therefore, the function would be positive and greater than 0. And where the function is below the x-axis, the y-coordinates would be negative. Therefore, the function values would be less than 0. So on the open interval from -3 to 4, the function is less than 0. And to the right and to the left, the function is above the x-axis, and therefore it's greater than 0. So in order to solve quadratic inequalities, what we're going to do is find the zeros of the quadratic function and then test each interval to determine whether it satisfies the original inequality. Let's go ahead and take a look at our steps. So step 1, we're going to find all of the zeros of the polynomial, or in this case the quadratics, and then arrange the zeros in increasing order. Next, we'll plot the numbers on the number line as open or closed points based upon the original inequality symbol. And then we're going to choose a test value in each interval to see if it satisfies the inequality or not. If the test value produces a true statement, the entire interval is true. And if the test value produces a false statement, the entire interval is false. So from that information, we can clearly graph our solution and then state the solution using interval notation or inequalities. Let's go ahead and try a few. So step 1, we'll set this equal to 0 and solve. This is factorable. The factors of -16 and add to -8, that would be -8 and a +2. So this function would be equal to 0 when x equals 8 and x equals -2. So we're going to use these two values to divide up the number line into our test intervals. And since the original inequality was less than or equal to 0, we're going to plot these as closed points. So we'll have a -2 and we will have a +8. Next, we're going to pick a single test value in each interval. So any number between -∞ and -2, let's say -3. A number between -2 and 8, let's just say 0. And then between 8 and +∞, let's say 9. Now what we're going to do is evaluate the left side of this inequality at these test values and see whether it's true or false. But to help us evaluate this, let's use our graphing calculator. We're going to press y equals, type in the left side of the inequality, x squared minus 6x minus 16. Next, we're going to use the table feature, but we want to make sure it's on ask mode. So if we press second window, make sure the independent option is on ask, and press second graph. And we're just going to type in our blue test values. We have -3, 0, and 9. Of course, we could do this by hand if we didn't have a graphing calculator. The y values represent the function values. So we'll compare these to being less than or equal to 0 and determine whether the interval is true or false. So when x is -3, the left side would be 11. So the question becomes, is 11 less than or equal to 0? That's false, which means this entire interval would be false. Next, when x is 0, the left side would be -16. Is -16 less than 0? And that's true, so this interval here would be true. And then lastly, at x equals 9, we have a function value of 11, and we already said 11 is not less than or equal to 0, so it would be false. So we have false here, true here, and false to the right. Let's go ahead and record that. This was false, this was true, and this was false. Since it was true when x equals 0, this entire interval is true, and therefore the solution to this quadratic inequality. Here's the graph of the solution. Using interval notation, we would have the closed interval from -2 to 8, and using inequalities, we would have x's greater than or equal to -2 and less than or equal to +8. Let's go ahead and check this graphically as well. We're going to graph the left side as a quadratic function and see where it's less than or equal to 0, meaning where is it below the x-axis. You can see it's below, between -2 and +8. And because it said less than or equal to, we include the endpoints. So there's the interval that satisfies that quadratic inequality. Let's go ahead and take a look at another one. First step is set it equal to 0 and solve. The second position must come from the factors of +12, where the inner and outer product must sum to -11. So if we put a -4 here and a -3 here, we'd have a -8x and -3x, and that checks. So we want to know when 2x minus 3 equals 0 and when x minus 4 is equal to 0. Well, here we'd have x equals add 3 divided by 2 and add 4 to both sides. So now we take all the real numbers and divide it into intervals based upon where the quadratic is equal to 0. So we have 3/2 and 4. And because the original inequality symbol is greater than 0, we're going to have open points this time. Pick our test values. Maybe we'll choose 0 here. This is 1.5, so maybe 2, and then maybe 5. And let's go back to our calculator now. Type the left side into y1. And again, we could do this by hand, but this is a very nice time saver. Second graph to the table, we'll type in our test values. They are 0, 2, and 5. And we're comparing these y values now to being greater than 0. So the interval on the left, 12 is greater than 0. That's true. The next test value was 2, produces a function value of -2. -2 is greater than 0. That's false. And the interval on the right, we have 7. 7 is greater than 0 is true. So the intervals are true, false, and then true. Let's go ahead and record that. This is true, false, and true. Which means our solution consists of the interval on the right, this interval, and the interval on the left, this interval. So using interval notation, it would be the interval from -infinity to 3/2. It does not include the endpoint there. And also from 4 to +infinity. Again, it's open on 4. Or if we want to use inequalities, we would have x is less than 3/2 or x is greater than +4. Let's go and take a look at it graphically now. We want to know when this quadratic is greater than 0, which means when is it above the x-axis. Let's take a look. We can see it's above the x-axis to the right of +4 and also to the left of 3/2. So our answer checks. Let's go ahead and try one more. Step 1, set it equal to 0 and solve. This one is not factorable, but we could isolate the x squared and extract the square roots or take the square root of both sides. We'd have x equals plus or minus, well, this would be 2i, which is not a real number. Now this is kind of a special case. There are no real numbers where this is equal to 0, so there are no values to divide up the number lines. So what that means is we have to pick at least one number on the number line and test it to see if it's true or false. So we can pick any real number that we want. Let's go ahead and pick a test value of 0, because we can do that without even going to the calculator. If x is 0, we have is 4 greater than 0. Well, that's true, which means the entire number line would be true, which means using interval notation we would have from -infinity to +infinity, or we could just state all reals. So graphically what that means is the graph of the left side should always be above the x-axis. Let's go ahead and see. And we can see this function is always positive, therefore it's always greater than 0, which verifies our solution. Okay, I hope you found this video helpful. Thank you for watching.